Okay, welcome to the true first video of this digital audio signal processing course. There were two previous ones, which were called I-DSP-0A and 0B. Those were just preliminary signals and systems DSP type stuff that you would need to know. So just a review, just out of courtesy. So this is where we really start. So throughout the course, we're going to be doing lots of DFT analysis of signals to see what they look like. So you really need to know what the pros and cons are and trade-offs and ins and outs are of DFT processing to do spectral analysis. So the idea is we have a signal and we want to analyze what it looks like in the frequency domain, its spectrum. We want to look at its spectrum. So in one of the review videos, I already showed you some of the mechanics of calling the FFT algorithm or the command within MATLAB and how to call that and how to plot the results and so forth, single-sided, double-sided. We usually do single-sided. We usually plot it versus frequency in hertz, and we usually, not always, but almost always plot it on a log frequency axis. So I've already talked about how to do that. So let's get into some of the details of using the DFT through the FFT algorithm. And then the next set of notes, the next video, will cover some of the ins and outs of the FFT algorithm. Not that you need to be an expert in FFTs to do digital audio, but you should know a little bit about it. So here's the scenario. We've got some discrete time signal. We'll call it X of n. And we're going to use the DFT via the FFT algorithm. So remember, the DFT is the thing and the FFT is just a fast algorithm to compute it. So we want to use those to analyze the spectrum of that signal or find its spectral content. How much energy is there at each frequency that's making up this signal? So here's the issues involved. These are true in other scenarios besides audio, but are particularly true in audio. So the problem with a Fourier analysis of music is that we think of music as something that has a changing spectrum, right? You play some notes at this time, and there will be certain spectral characteristics during that interval that those notes are played, and then immediately after that, you play some different notes. And so the spectrum is going to change. Now, that doesn't mean that we can't just treat the audio signal as a whole and think about its whole aggregate spectrum. We can do that, and sometimes we do. But sometimes we kind of want to zoom in on little chunks of time of an audio signal and look at its spectrum and see how it changes. So that might be the case if we're trying to use spectral analysis to maybe automatically determine what notes are being played. So that's an audio DSP application. We don't talk about it in this course, but that is one, and it's very exciting and interesting. You can take a piece of music, digitize it, put it into an algorithm, and it will analyze it using DFT approaches to determine, oh, this note was played at this time and this note was played at that time. And so after this video, I'll post a second example, or just an example video that talks about how to do that for a particular piece of music. So here's the issue because of that, because the spectrum is changing with time, and it's changing fairly rapidly, right? Every beat of the music, probably, it's changing. So we might want to look at this on a block by block basis. Maybe we'll overlap those blocks. We'll talk about that at the end of this note set. But the issue is that the blocks are necessarily short, and that's a problem with DFT analysis, as we'll see. And maybe you've already learned that in your signals and systems class or in a DSP course. So that's a consistent thing that's talked about in a lot of DSP scenarios. And the thing that we see in those analyses is that when we make the block short, so in other words, we try to take the DFT of just a short chunk of data, the resulting spectrum has what I call smearing and what a lot of books call leakage. It's the same thing, it's just two different words to describe the same mathematical function. And there are reasons why we sometimes might call it leakage and sometimes might call it smearing. But in this scenario, I like the word smearing, so I tend to use that, although I do let the word leakage leak in every once in a while. Okay, so let's set up the mathematics of this. So suppose we've collected some short block of data. We've got some signal that we've collected. Maybe it's just an audio signal and we've collected data, over the duration of one beat, and we think there's a note that's being played in that chunk. Now, we can imagine that that short block of data came from some much longer signal, and for the purpose of our mathematics, we'll just assume that it's some infinite duration signal. It just helps us not have to worry about how long is that longer signal. It doesn't really matter how long it is. And I say over here that in audio scenarios, there really is no such signal, because we just got done saying that there isn't a signal that kind of persists for a long time that has the same spectral characteristics of that short block. So we have to at least imagine that there is some signal that would be a natural extension of that note that's being played in the block, for example. So we could imagine that maybe that note just is held forever. So that's the idea. This is just setting up the mathematical scenario that will allow us to understand what happens when we do this kind of processing. So here's our math model for what's happening, for how we think about the collection of this short block of data. Here is some infinite duration signal. And like I said, we have to at least imagine that there is some infinite duration signal. And this represents the samples that we've collected. And for mathematical purposes, to apply the theory of Fourier transforms to what we get from the DFT, that's why we're setting this up here. We have to imagine that the data that we got outside of that should be treated as zero. And so this little window, that's why I use a W there. And here we're imagining that window to be a rectangle. It's 1 over the range of samples that we're collecting. So we're collecting n samples. And then it's 0 outside. So you can see the multiplication effect of that makes this finite duration signal be 0 outside the range that we're imagining collecting it. Now, physically, all we do is just collect samples. Mathematically, we model that as, okay, outside of our collection zone, the math is going to have to assume that it's 0 out there. That's just how the math works. And so the subscript R here is because this looks like a little rectangle. Now, subsequently, we will look at other shapes of windows and see the advantage of using those. But for now, this is our model. We apply a rectangular window to some infinite duration signal. We don't really have to do that multiplication. When it's a rectangular window, it's just the effect of collecting. But if we're going to use some other shape of window, then after we collect with the rectangular window, we multiply by some non-rectangular window to get the applied window shape that we want to use. And we'll talk more about that in upcoming slides. So here's the implication of that. This is why we set this up this way, is so that we can use a theorem from the theory of DTFTs, discrete time Fourier transforms. These are things that we can't really compute numerically. So we think about what's going on in terms of those so that we can interpret what we get from our numerical DFT computations. But the DTFT is our theoretical thing that we think about. So there's a theorem for that that says if you multiply in the time domain, the result is the convolution of those two DTFTs convolved together to give the resulting signals DTFT. So I put a subscript here, W, to represent the DTFT of the windowed signal. I got rid of the sub R there. This superscript F here is to help us remember that this is a DTFT. Why I used an F there is not really terribly important, but we'll use that to at least sometimes to indicate a DTFT. So we're convolving the DTFT of the infinite duration signal with the DTFT of the applied rectangular window. And this symbol here is a special kind of convolution. Because DTFTs are periodic, we have to do what's called a circular convolution. And we'll revisit circular convolution again later in the course when we talk about overlap save and overlap add things. And so here is the actual mathematical form for that convolution. Now, relax. We do not really have to do that convolution ever. It's just something that we use to think about. So when we convolve two things together, this thing is going to cause a leakage or smearing in that to show up in that. And we'll look at some examples to illustrate what I mean by that. So what does this thing look like? What does this rectangular windows DTFT look like? And I should point out, I'm using theta here as our discrete time frequency. So that's in radians per sample. In previous notes and in subsequent notes, I will, instead of theta, I'll use omega. So there will be a few times where I use theta, and that's because I'm drawing these notes from a book by Boaz Peratt. It's a DSP book, and he uses theta. And so I taught out of that book at one time, and I had these notes, and I didn't want to have to go through and edit everything. So theta is our discrete time frequency. We look at it from minus pi to pi, and it's 2 pi periodic outside of there. So what does the DTFT of the rectangular window look like? I'm going to go through this pretty quickly, but this is pretty straightforward. We write out explicitly the DTFT of that. That's just by the definition of the DTFT. And then we say, this looks like the form of a geometric sum. You can look that up on Wikipedia if you want. And if you apply the formula for a finite duration geometric sum, you get this result. And now I'm going to do a trick that shows up lots in DSP stuff. I'm going to factor this out of the top, and I'm going to factor this out of the bottom. And the reason that I'm doing that is so that after I factor each of those out, I get something that is a plus j blah and minus j blah. And I'm just using blah here as whatever is there. And then down here I see a j blah and a minus j blah. And I have a negative sign. So look, this is setting up Euler. And Euler with a negative sign here is for a sign, and I need a 2j. So I throw the j in there. And I throw the 2 in there. And the fact that I put it in both places means I don't have to account for it anywhere else. So now I'm all set up to use Euler, and that's how I get these signs. So now I get sine over sine. But here's the thing. This sign wiggles much faster than this because of this n here. You can kind of think of that as, I know it's weird, but that's the frequency along the frequency axis, right? So if n is a number bigger than 1, that top is going to wiggle faster than the bottom. In fact, the bottom hardly wiggles at all over the minus pi to pi range. We're going to give this thing a name. This is what Peratt does in his book. We're going to call it d theta comma n. I would actually prefer to put the n as a subscript, but Peratt puts it as a argument. And so I just kept that. And that's going to be called the Dirichlet kernel. And this thing out in front is just really a linear phase term. So the real nature of this DTFT lies in the Dirichlet kernel. So let's take a look at what that thing looks like. So I'm just plotting the Dirichlet kernel here. It's real valued It's going to go plus and minus. So it's not quite like I'm looking at the magnitude of the DTFT of the window, but it's almost. If I were looking at the magnitude, that e to the j thing out in front would go away, and all of these things that go down negative would pop up. So just keep that in mind. But one thing we see is, that looks kind of like a sinc function. Why? Why does it look like a sinc function? Well, if we go back here and we remember a small angle result for sine. So when theta is small, sine of a small angle is approximately equal to that angle. So now we get something that's like sine x over x, almost. So it's very much like a sinc function. And so we see that sinc characteristic here. So we've got the big peak at 0, and then it wiggles up and down. But remember I've divided by pi here, so I've normalized. So this is really pi, and so there's our beloved minus pi to pi, and it's periodic outside of that, and you can see that. So it's like a sinc function, but it has to, out near the minus pi and pi, it has to start behaving in a way that will let it start all over again. So it doesn't quite go all the way down to 0 like a real sinc function does. Now, some other things that we can see here, I've done this for two different n values, 11 and 41. We call this the main lobe of our window DTFT, and we'll talk about those main lobe characteristics a lot. We see that as n goes up, the main lobe gets narrower. So this is for n equal to 11, and this is for n equal to 41. So we can see that the width of this main lobe is narrower. However, we measure the width of that. Now we're actually going to measure it here 0 to 0. So we can see that 0 to 0 width gets narrower as n goes up. The other thing that we see is that the side lobes get lower in some sense. So the side lobes are these things out here. So again, remember, we can think about the magnitude of this if we flop those things up. So those side lobe levels are going to be lower here for a larger n. And then the other thing that we see is that the height of the main lobe actually equals n. So this height is actually at 11, and this height is at 41. So all of these things combine to tell us that this Dirichlet kernel, that's the DTFT, or at least the essence of the DTFT of the rectangular window, this is the thing that gets convolved with the actual infinite duration signals DTFT to give us our resulting finite duration signals DTFT. So it looks more and more like a delta. And we also know that convolving something with a delta just gives us back that same thing. So the more this looks like a delta, the more the DTFT of the collected signal looks like the DTFT of the infinite duration signal. So that's all good. And so now this, as I click through here, you're going to see some of the definitions that we apply here. So we define the nearest 0, and you can figure that out by looking at those sine over sine thing. If you look at the numerator, you can figure out it goes to 0 at integer multiples of 2 pi over n. So the first one is at 2 pi over n. And then we define the main lobe width as from 0 to 0. So that's twice that. So that's 4 pi over n. And then we can also see that the largest side lobe peak, and so I show this going down, but again, remember it should, we should think about it as going up. If we convert this height into dB and convert this height into dB, the distance between them is minus 13 dB. And that's true for any of the, for any n value. So you might wonder, like, hey, what's going on? I thought we said that the side lobes get lower and the height goes up. Yeah, that's true in a loose sense. The main lobe does go up. And the side lobes, at least out here, go down, but this level flipped up relative to this level is always 13 dB down. So keep that in mind. Let's look at the impact of this. And here I do use the word leakage because that kind of makes sense in this scenario. So we're going to look at two complex sinusoids, not because we're particularly interested in complex sinusoids. It's just a little easier to visualize what's going on. So we've got an e to the j theta 1n and an e to the j theta 2n. So those are sinusoids. You look on your DTFT table and you'll find that they go to delta functions, and the delta functions are located at the frequency of each sinusoid. So it looks like this down here. Now, these are true continuum delta functions, so technically these go to infinity, but we have a habit of showing on plots the height of these things to represent the number out in front. So this height will be proportional to A1, just graphically showing it, not literally mathematically. And then graphically, we have that height be relative to A2. So in this case, we can see that if this is at position theta 2, this height here is A2, we can see that the second one is weaker than the first one. And you can also see that from minus pi to pi, there's just one spike for each. That's the nature of doing complex sinusoids. And then we see the replicas out here. And so that's it. That's what that thing looks like. Now, we're going to imagine collecting a finite number of samples from this and computing, or at least imagining, what the DTFT looks like for that finite duration signal. Now, we could find that analytically by using a geometric sum and so forth, but that's not going to help us interpret what's really going on. We instead use the theorem that says the DTFT of a finite duration signal is going to be the infinite duration signal's DTFT convolved with the DTFT of the rectangular window. That's, think, the Dirichlet kernel. And so the other thing here is that a result that says anything convolved with a delta function located at alpha will just take that thing and shift it by alpha. So that's a result. So this thing has delta functions in it. So it's going to take this thing and plop it down there. And it's also going to, the second delta function in here, I said that backwards. There's a delta function, two delta functions in there. One of those is going to take this and plop it down at theta 1. And the other one is going to take the window DTFT and plop it down right there. And so here's a little picture of that. I've color-coded those so that you can see them separately. But in reality, what we see is the sum of those. So here's an insight that you need to be aware of. So this is called side lobe leakage, but it's also called side lobe interference. And here's the thing. Because we're imagining this second sinusoid to be weak compared to the first sinusoid, the first sinusoid has a high main lobe, and because it gets multiplied by the A1 out in front, and the second one has a lower main lobe because it gets multiplied by A2. So remember, the W by itself, the main lobe height is the same, but then the main lobe heights get adjusted. So now this literally is the height of these, not just a graphical essence that we use, but now we see physically the height difference. But here's the thing. Notice that that red main lobe is embedded in a bunch of side lobes for the stronger signal. So if I didn't know that the red one was there, and I added these things together, I might not even be able to see the remainder of that red main lobe. So if I were to look at the DTFT of this finite duration signal, I won't see that there are two different sinusoids there. I would maybe only be able to see one. So think about it. Musical notes can be thought of as roughly over a short period of time as like a periodic signal. And so we would expect there to be harmonic spikes. Think Fourier series. So musical signals will have harmonic spikes if we look over a short enough period of time. And if those harmonic spikes are weak compared to the fundamental, when we do this short duration signal DTFT, we might not be able to see those harmonics, and that might be challenging for us to deduce what's going on. So I don't show the actual sum of these, but I think you can imagine what that's going to look like. So this is called side lobe leakage in general, but I like to call it side lobe interference. So it's not quite smoothing, although we do see that each delta function becomes smoother in some sense. So there's smoothing going on, and then the two different sinusoids interfere with each other. The side lobes of the stronger one can obliterate or obscure the main lobe of the weaker one. And so that's a problem. And so we want to try to address that. Here's another scenario. Now we've got two complex sinusoids, so same setup as this, except now we're picking theta 1 and theta 2 to be closer to each other. Here they were fairly far apart. And we're also picking A1 and A2 to be close to each other, whereas here they were somewhat different from each other. So here is the DTFT of the infinite duration signal. And now each one of those, if I collect a finite number of samples of this, each one of those delta functions is going to get converted into that sync-like thing. And so there I show them. And their heights are the same, or at least close to being the same. And so their main lobes are about the same height, and their side lobes are about the same height. And so now that's what we get for each of them. I say theta sub I. So I'm showing them individually, but remember, those really get added together. And so there is the result, is that purple line there. And I think I show it down here. So that's the result of, that is the DTFT of the finite duration collected signal for this scenario. And do we see two sinusoids? No, we see just one big peak. So to us, it looks like, oh, maybe there's just one sinusoid there. This might show up when there's two instruments trying to play the same note. And so their fundamental spikes are close to each other. Or maybe a 12-string guitar with two strings tuned in unison, where some of the strings on a 12-string guitar, some of the pairs of strings are tuned to the same note. So if we're trying to do analysis and determine, was this a 12-string guitar, or are there two people playing the same note? We might not be able to see that because of this, what I call main lobe smearing. The two sinusoids give two different main lobes that just smear into one. It's sort of like, looking through fog at two closely spaced lights. They might just blur into one big blob, and you don't know that there's two closely spaced light bulbs there. So that's what I call main lobe smearing. And so we can see that sometimes in audio, that is an issue. So we see that both of these issues come from characteristics of the Windows DTFT, that Dirichlet kernel. And we see that one comes from side lobes being too high. That was the first example. And the other scenario comes from main lobes being too wide. So we really want to make each of those things be less of an issue. But we've already seen that increasing the amount of samples that we use will fix both of those. So if we can do that, that's ideal. But in a lot of musical applications, we can't because we're trying to zoom in on a single note played over a short duration. So we want to come up with some schemes that allow us to address this. And that will lead us to looking at other than a rectangular window, and we'll see that shortly. Just want to spend a little bit of time talking about the connections between three different Fourier transforms, the CTFT, the DTFT, and in fact, we'll see two of those, and then finally the DFT, the one and only thing that we can actually compute and look at. So let's walk our way through this scenario. This is just illustrative. So suppose we have some sort of music signal, and we're interested in identifying where that spike is. Maybe that will tell us what note is being played. I have to sample that continuous time signal at some sampling rate fs, and I see here that I've picked an fs in this example such that fs over 2 leaves a lot of the original spectrum outside of that range. Remember, these two things get mapped to minus pi and pi on the discrete time frequency axis. So we also know that anything up here will alias down into this region once we do the sampling. So we're setting up a scenario here where we expect there to be significant aliasing. So we're going to walk through our concepts here and then tie it to the actual practice that we can do. So the next thing is we first imagine that this is some infinite duration signal. Even if it isn't, we at least imagine that it's been continued out to infinity in some natural way. So if it's a note that we've collected, we're at least imagining that that note could be continued on in both directions infinitely long. Then we sample this, and we imagine that we have infinitely many samples here. That's why I have a sub-infinity here, and why I say full. So the full means I have the full infinite duration signal. Again, in the real world, we can't have that, but this is our thinking. So if we look at the DTFT of that, there is going to be aliasing in this case, because remember, this part, when we shift this whole thing up to create the first spectral replica, this part ends up right here. And when we shift this down by fs to create the first replica to the left, this part ends up over here. And so we can think of that as drawing a line here and folding this back and folding this back. And that's what creates this elevated level here. That's aliasing. So if we had no aliasing, this DTFT should look almost exactly like that if we've made the aliasing virtually negligible. But we have aliasing error here, which I've exaggerated. I've picked an FS that leaves some significant stuff up there. And in fact, the level that I show here is even exaggerated for the amount that I've left. But that's the idea. So with aliasing, we've already made an error. And so the thing that we're looking at is not quite exactly what we were looking at. But if our job is to just figure out where is that peak, maybe we haven't done such a bad job. We can let some aliasing happen out here as long as this peak looks like this peak and is in approximately the same location. Okay, all good so far. Now remember, we cannot collect infinitely many samples, and in fact there isn't really infinite duration signal to actually collect anyway. These things are thoughts. But now what happens is we collect n signal samples. And now we have x sub n. So I'm using that here to represent the DTFT of this n sample collection. I also call it the truncated signal DTFT. It's not the DTFT that's being truncated. It's the signal going into the DTFT that gets truncated to n samples. Okay. Now, from our theory, we know that this thing gets convolved with the main lobe and the side lobe, and there's going to be some smearing. Now, it won't really look like that. I just kind of drew this in PowerPoint, but I'm showing the essence of what's happening. So one of the big things that happens, remember how we saw that the really sharp delta function got smeared out into a wider main lobe? Well, this really sharp thing is going to get smeared out into a wider bump. So it won't be as pronounced. It won't go up as high. And in fact, this valley here will get filled in. Now, there might be some other wiggling in this, but this is the basic idea. And that's why I put this in quotes. So this is kind of a cartoon of how things are actually working. But it's how we think about it. Now, remember, we can't really see any of those in the real world. It's all thought. It's all thinking. Our job is to collect these samples, put them into a DFT computation, get the DFT values, and plot these. So in one of the review videos, I talked about how to properly create your frequency vector and plot those one-sided or two-sided. And if you're doing one-sided, how to plot them on a log frequency axis. I'm going to show two-sided because that's what we've been doing here, because we're talking more theory and interpretation. But what ends up happening? Here is the most important thing on this slide. The computed DFT is just a bunch of points. So that's these little red dots, and I'm showing them as kind of a stem plot. And you can see that since it starts at minus pi, I've done the FFT shift command that I talked about in an earlier video, one of the review videos. And we also talked about the spacing between these. The spacing would be 2 pi, this distance, divided by n, the number of points that we end up computing. And so in this example, it looks like I started with 8 samples and I computed 8 DFT points. That's very, very small compared to what we do in real life. Normally we do thousands of DFT points, but it's hard to see those in a little cartoon version. So here's the important point. I said, here's an important point, and then I never said it. Here is the important point. These dots that correspond to the values of the DFT lie on this DTFT, the smeared DTFT of the truncated signal. So that's what this dashed curve is here. It's this, okay? So that's why we go through this progression. We go from the CTFT to the full DTFT, we see the effect of aliasing. We go to the truncated DTFT, we see the smearing, and then finally we compute the DFT and we just get points, and I call that the grid error, because we're going to miss some things, right? If all we had were those points, we're tempted to just draw lines between them. And do we see the peak? We cannot really see that peak. It's been obliterated by smearing. It made it through the aliasing okay, but between the smearing and the grid error, the peak is gone. So we are not able to, in this simple little cartoon, collect 8 samples, look at them and find where that peak is. Just can't do it. So what do we need to do? Well, we need to minimize the aliasing. Okay, maybe we're okay with that. Minimize the smearing so that this peak is more pronounced, and make sure we compute on a finer grid so that we can see the peak that's in the smeared one. So that's what we need to do. So this just summarizes those errors. These are the 4 things we just talked about. These 3 are thought things. This is a doing thing. Okay, so thinking things, doing things. So we go through the course, there's going to be a lot of that. This is a thinking thing, and this is a doing thing. And we almost always do the thinking so that we can understand what's happening in the doing. So we have the aliasing error, and really the only way to control that is through proper choice of FS. Okay, maybe an anti-aliasing filter, but even with the anti-aliasing filter, we need to make sure that we're retaining the range of frequencies of interest, and then we choose our sampling rate properly. Then we have smearing error, and we can control that through the choice of number of samples we collect. And so the more samples we collect, the less smearing there is going to be. But we've already said we may be limited with how many samples we can collect. So we might need to choose a window that is not a rectangular shape. And that's where we're heading. We'll see how to do that shortly. And then finally, grid error. And yeah, our N choice will control the grid error to some degree, because as we collect more samples, we're going to get closer spacing on our DFT points. But we already said we may be limited on our N choice. So we're using a window to help with that. And then we're going to use zero padding to help with the grid error. And zero padding is just a cheap and dirty trick that comes out of the theory of this and allows us to get any grid spacing that we want. Does not change the shape of this. I'll say that again. Does not change the shape of the underlying DTFT sub n. All it does is gives you a finer grid on that. So that DFT is the only thing that we can compute from the data. And it's got all of these errors in them. And then I guess I didn't put it down at the bottom. The zero padding, on some of my notes, I have a little discussion of zero padding down here. I think I did that in the review video. But the idea is, if we were to collect this many samples, remember we were talking about 8 samples. Suppose we put 8 zeros at the end. Now we're going to actually get, so we'll have 16 points here, and we'll get 16 points here, and they will be spaced half the distance that we had before. So that just means we get points in between the points that we had before. And what happens if we then, instead of putting 8 zeros here to take us to 16, let's put a bunch of zeros there to take us out to 32. Now we'll have a quarter of our original spacing. And we don't have to limit ourselves to powers of 2, but that's common. So all that does is gives us a finer grid. It's just a cheap and dirty trick that we do. Okay, so keep all of that in mind. Those are key ideas to understand to make sure you know what's going on and what you're seeing in the DFT. We collect samples, we apply a window, we zero pad. We zero pad after applying the window. Do not zero pad, then put the window over everything. Nope, that won't work. Apply the window, zero pad, compute the DFT, and our job is to see if we've done everything right. The thing we see there should look a lot like the original CTFT, and hopefully we should be able to see peaks and guess where notes are and things like that. So this window, the impact of the window we saw comes by, or we understand it by looking at the DTFT of the window. And so for the rectangular window, we saw what that thing looks like. And we pulled out some characteristics of this DTFT of the window. In fact, we were just looking at the part of it, the Dirichlet kernel part of it. But we talked about the main lobe width, which is measured 0 to 0, as we talked about before. There's a few alternate measures of main lobe width, but that's the most common. Side lobe levels, and the thing that we care about is the highest side lobe, which is not always the side lobe that's the closest to the main lobe, but it's often the side lobe that's closest. There's a few weird window shapes where the highest side lobe is not the closest one to the main lobe. So the highest side lobe, and then how fast do they drop off as we move further from the main lobe? And it turns out that these two things exist in a trade-off. That's almost always the case in, in the real world. If we try to lower the side lobe heights, we will necessarily widen the main lobe, and vice versa. If we try to narrow the main lobe, we will necessarily raise up the side lobes. This is all holding N fixed. This is by picking other shapes for the window. So let's take a look at this. Here's the rectangular window that we've already talked about. And as I said, we don't really explicitly apply a rectangular window. It implicitly happens when we collect N signal samples. If we want some other window shape, after we've collected the samples, we must multiply by the window shape. So we've already looked at this rectangular window. Here we're looking at the magnitude of it, and we're doing it in dB. So, and I should point out that I should say it over here, but I've normalized this so that the main lobe height is at 0 dB. We already saw that the height is really in non-dB at the level of N, but I've just divided these by N so that I get 1 in non-dB and then 0 in dB. And so here's the highest main lobe level. And we can see that as we move further away, they drop off initially with some sort of slope here, and then they kind of level off. So we're interested in this highest level, and we're also interested in this slope of drop off. So if we were to analyze this, we already quickly looked at the main lobe width. We'd see that these 2 points here, where it goes down to 0. So remember, 0 in dB goes to minus infinity. So that's why there's these seemingly vertical lines here. They're shooting down to minus infinity, which is, I'm not able to show that on the vertical axis, obviously. So that width is 4 pi over N. So N is the length of our collection, or equivalently the length of the window. And we'll see that that's actually good. That's the best that we can do. We'd like to do better than that, but it's theoretically impossible to get a main lobe width narrower than that. And then the other thing, we don't go through the analysis here, but one could, you'll find that regardless of the N value, this side lobe, the highest side lobe, is always 13 dB down from the main lobe. And this rate of drop off here is on the order of minus 6 dB per octave. So remember, an octave is a doubling of frequencies. So if we start off here, maybe we're at 0.1 pi, and then we go to 0.2 pi, that should drop off by 6 dB. It's not necessarily from side lobe height to side lobe peak, or side lobe peak to side lobe peak, but if you just kind of draw a line along the top, you'll see that it has that slope of approximately minus 6 dB per octave, except when we start getting out here. Okay, so keep those in mind. The width, 4 pi over N, largest side lobe height, and the drop-off rate. Okay, now we're going to just introduce some of the common windows here. Some of them are named after people. In fact, almost all of these are named after people. So there was a guy named Han or Han, I'm not sure how it's pronounced, and there was a guy named Hamming, and they each came up with windows. So Han came up with his window first, and then Hamming said, oh, I see what he's doing. He's got a 1 and a cosine thing, and we'll see what these look like in the time domain in just a little bit. And then he essentially weights each of those by 0.5. And what Hamming said is, well, let me pass that 0.5 through and then tweak it a little bit to try to get a little better window. So we'll see that. And so here we can see some characteristics. This is in the time domain. So this is literally the window values that we multiply our collected signal samples by. So this is a point where students should go, wait, what? I collect a bunch of signal samples, and then, so here's my signal sample range that I've collected. So whatever I've collected over that range, The ones in the middle get multiplied by 1, but the ones at the beginning and the end of my collection get discounted a lot. And in fact, even with the hand, the first and the last sample get multiplied by 0. What the hell is going on here? Why would I do that? Well, you can't make sense of it from the time domain view. Let's look at what the kernels look like. So I didn't label my y-axes here, but I think you get the idea. So this is the Hamming window in the time domain. This is their DTFT versus frequency theta. I'm using theta here in radians per sample. So let's see what we got for this seemingly bizarre activity of multiplying our collected samples by numbers much less than 1. Well, what did we get? Let's look first at Han. So Han was first, and we have a 32 dB down instead of 13 dB down. Remember the rectangular window, the first side lobe was at only 13 dB down, and now we're 32 dB down, and it drops off rapidly. Drops off minus 18 dB per octave. So if we were to compare this to the rectangular window, this would already be very low compared to the minus 13 dB, and that would drop off slowly, and this drops off rapidly. So we've controlled the side lobe interference effect, right? If we have a fundamental and a harmonic, the likelihood that the side lobes of the fundamental interacting with the main lobe of the harmonic is less with the Han window than with the rectangular window. So let's see what Hamming got. Hamming said, okay, Han did an interesting thing here, and I'm going to tweak. So the 0.5 goes to 0.54 on the 1, and on the cosine, it goes to 0.46. What did he accomplish? The highest side lobe, which notice is not the nearest one to the main lobe, is now minus 43 dB down. But there was a price to pay. Instead of dropping off at minus 18 dB, it drops off very, very slowly. But it starts off much lower. Okay, all that's good. There's a price to pay for both of these, though. The main lobe width is worse than the rectangle. It's twice what it was for the rectangle. The rectangle window had a main lobe width, MLW, of 4 pi over n. This is 8 pi over n. So Han and Hamming are saying, if you're willing to give up some main lobe width, you can get better side lobe performance. And in many applications, especially if you're saying here's a fundamental and here's a harmonic, we might care more about side lobe issues than main lobe issues. So there's 2 windows. So we would literally collect our samples and then multiply those values times the sample values, then zero pad, then compute the DFT. Okay, there's lots of other windows. We just looked at Han and Hamming. And this is a paper by Fred Harris way back in 1978, where he did a very thorough analysis of dozens and dozens of different windows. Every one of those little circles on here is a type of window, and I've labeled a few of them, the Hamming and the Han that we just talked about. And then there's some other people's names there, Blackman, Dolph, Kaiser. There's nobody named rectangle, and there's nobody named triangle. Although triangle does have a separate name. It's called the Bartlett window, but most people just call it the triangle. And then there's a bunch of other ones here that I didn't put any names on. You'll also see that for the Dolph and the Kaiser, there isn't just one, there's several. And in fact, if we were to draw a line, we could get anywhere along that line for the Dolph. And if we drew a line through the Kaiser ones, we could hit anywhere on that line for Kaiser. So Dolph and Kaiser are an adjustable family of windows. And I should point out that Harris measures the main lobe width in terms of a 3 dB bandwidth rather than 0 to 0. And he also puts it in units that he calls bins. It's not important. Just think of this as some alternate measure of main lobe width. So we're looking at highest side lobe level versus main lobe width. The thing that's missing from this is the drop-off rate. So we're not seeing that here. Okay, but you can see the rectangle is way up here. It has the lowest main lobe width, but also the highest side lobe widths. And so hand took us to here, and hamming took us to here. Ideally, we'd like to be down here. What's this gray line? It's a boundary line. We can show that that is the theoretical line that you cannot get down here. So you can see everything kind of lives on that line. The rectangle, it kind of looks like it's off that line just a little bit, but maybe that boundary curves just a little bit. But that's the basic idea. Okay, let's take a look at some applications of windows and see what happens. So here's a single real sinusoid. So unlike our example earlier where we had two complex sinusoids and we saw two spikes, this is one sinusoid and we're seeing two spikes, one at the positive frequency and one at the negative frequency. Also, this is coming from Proacus and Monolacus. They use the lowercase omega here. Damn, I should have fixed that, but I didn't. I tend to use capital omega here, or theta, as I did in the previous ones. But Proacus and Monolacus like to use the little omega here. It's still in radians per sample. You can see I have the capital omega here, so I probably should fix that, but I didn't. And then here's the code that I used to make this, the MATLAB code. So you can play around with that, change the number of samples. So in this case, L is what they use to represent the number of samples, whereas previously I used N. And then they zero pad to a ridiculously large value so that these curves look nice and smooth. That's a little excessive, perhaps. And so we do the FFT shift and we do the little trick that I showed in the review video for plotting this. And then I use a ylim command to limit the range of the vertical axis. So that's with a rectangular window. And then here it is with the hand window. So notice that the effect of the main lobe is this, right? Remember, the main lobe of the window's DTFT gets moved to the location of the frequency component that it's being convolved with. So remember, that convolution happens in the frequency domain. We don't do it. We do the multiplication in the time domain, and that convolution just theoretically happens and shows up in our results that we compute using DFTs. So we've got wider main lobe, but our side lobes are a lot lower. So if there were another sinusoid out here, we might not see it in the rectangular window, but we might see it pop up in the hand window. And I think I show that on some subsequent slides. So as we said, the rectangular window is really horrible at finding a weak harmonic in the presence of a strong fundamental. And in music analysis, that's what we want to do a lot. Okay, here are some other examples. Here are three different sinusoids. So again, I left the omegas here. It would be better if all of those were omega 0, omega 1, omega 2 with capital omega. And I don't do quite as much zero padding here, but it doesn't really matter. And so now we're looking at two scenarios: rectangular window, Hanning window. Whoops, what happened there? And Hanning window, all with zero padding out to 2048 samples. So I'm not showing the code, but you should be able to figure out how to do this. And two different collection sizes. So earlier I was using capital N. Proacus and Monolacus use L here. So now we can see what's happening. Let's just look at the rectangular case. We can't see, notice that these two sinusoids are very closely spaced in frequency. And with 50 collected samples, we we can't see those two close ones. But when we go to 100, we can see those two spikes. Now, when we go to the Hanning window, when we go to the Hanning window, we still can't see the two spikes there for two closely spaced sinusoids. And fortunately, when we go to 100, we can still see that. But now, notice it's not really there, but if there were some other frequency popping up there, we'd never be able to see that here or here. But we can see it here, and we can even see it here. So you could rerun this example where you make, you choose different frequency values here and put different amplitudes on those and play around to see when you can and when you can't. And you'll see that the Hanning window does allow you to see these weak things because it's knocking the side lobe levels down. So here is an application to music. So what I did was I played the low E note on my guitar. I think I say 82.41 hertz. I think my guitar was a little bit out of tune here. I don't think that's the actual correct frequency for a true concert pitch low E on a guitar. I could be wrong, but I think I was a little bit out of tune. And so now I collected 16,384 points. So I just plucked it and I let it go, probably sampling at 44,100. So 16,000 versus 44,000. So maybe about a third of a second that I collected this for. And then I processed that either with a rectangular window. So I just collected the samples and zero padded, or with a Hanning window. I applied the Hanning window to the 16,384 points and then zero padded, and then computed the FFT and plotted it, and only show up to 2,000 hertz in both cases. So this is a single-sided spectrum, non-log axis. So when we're looking for harmonics, putting it on a linear axis is actually helpful. If we're not looking for harmonics, then log axes might be more helpful. So we can see the fundamental here. And remember, pseudo-periodic signals like a string being plucked on a guitar vibrates back and forth, creates something that's kind of periodic. So from Fourier series, we expect to see integer multiples of that fundamental frequency. So we would see something at around 82, and then so 82, 164, and then 3 times 82, whatever that ends up being, 240 something. That's there. So these spikes are spaced every 82.41-ish hertz. And with the Hanning window, we can see lots of spikes there. But notice with the rectangular window, it becomes a little dicier to see them. We can see all of these strong ones still, but we get up here, and here we can clearly see a harmonic there. And here, I don't know, is that really a harmonic? And then here we can see, oh, something weird is happening there. It looks like there's kind of like a double harmonic. And that's probably true, because remember, I only said that the string is pseudo-periodic. It's not quite. It's decaying exponentially-ish. And there's some, string physics going on. But down in the rectangular, I can't even really tell. Is that really something there or not? And now you start getting up here, I can still see things spaced on the harmonic range, but now I'm just, I don't know whether I'm seeing anything real here or not. So this is clearly showing, for this application, the advantage of the Hanning window. So look, there's lots of different windows. Hanning are some of the most common ones. There's other ones you can explore and try out, but they're all aimed at giving up main lobe width. You can see that happening here. Giving up main lobe width for better side lobe characteristics. So some people like Hamming, some people like Hanning, Some people like Kaiser or Dolph. The Dolph is also called Chebyshev or Dolph Chebyshev. Some people like the Blackman. Some people like the Blackman Harris. There's dozens and dozens of these things. Okay, so let's forget about that for a moment and go back to thinking about a limitation of the kind of DFT processing that we've been doing. And I've been alluding to this by saying, oh, the music note is, the notes are changing with time. And so, if we collect over a long period of time, we might be collecting multiple notes. Now, I will admit this is not an audio example. I used this example when I taught a course on using Fourier analysis for analyzing radar signals. So this is more like a radar signal, hence the microseconds here. But you get the idea. A signal has a note played at a certain frequency, then maybe a lower frequency, then back to the same frequency, and then an even lower frequency. Now, the other thing you'll note is you can especially see it here. It looks like the frequency is going up. So imagine like a trombone going burp. So that's actually happening in each one of these. So maybe we're analyzing a really, really fast trombone because we're talking microseconds that's going burp, burp, then lower, burp, burp, burp. Really low. I should have started a little higher. So maybe that's what we're trying to analyze. And we'd like to be able to use Fourier analysis to see those changing frequencies, that burp nature. Okay, so suppose we collect all of this. So imagine this isn't necessarily microseconds, but maybe seconds. Okay, although these would have to be faster. So maybe these are, I don't know, forget about the units. If we were to collect all of this and take a DFT of it, we'd get a spectrum that looks like this. And what does that tell us? Well, we're seeing that there is more content around 7 megahertz. Yeah, this is clearly not audio. We're seeing a lot of strength around 7 megahertz. We're seeing some around 5 and the weakest around 3. So what does that tell us? If we hadn't seen this, does that tell us what we actually would be hearing if this were not a radar signal or we had radar hearing? So the DFT is correct. It's mathematically correct, but it does not show us this kind of joint occurrence in time and frequency. So we're seeing during this interval, there is a certain frequency range that's happening. And during this next interval, there's a different frequency range that we're experiencing, just like in music. So what we would really like is some sort of time frequency joint representation. So let me explain what's on this bottom plot. It's really 3 axes, a time axis, a frequency axis, and coming out of the page or the screen, a height. A third axis would be the magnitude that corresponds to how strong it is at each of these frequencies. So let's look. What is this telling us? At 2 microseconds, we see something start around 6 megahertz and do the trombone up to 8 megahertz over 1 microsecond. That's what we're seeing up here. You can kind of see it starts a little lower frequency than it ends at. And then at 4, between 4 and 5, we see a brup that starts at 4 and goes to 6, right? We can see that this wiggles a little bit slower than that does. Then we see this looks exactly like that. So yep, we're right back to brupping between 6 and 8. And then finally, this is the lowest frequency of them all. And we see, yeah, it starts off down around 2. And so since these are all the same height, we would expect along this line, the height coming out of the screen would be roughly the same height. That would be the ideal. This is a more desirable time frequency representation. And there are entire courses talking about this kind of mathematics and how we would do that. So this would show us sort of like a musical score, right? Time is moving this way along a musical score, and the note value, higher frequency up, lower frequency down. A trombonist could read this perhaps and say, okay, I'm going to start a note at that frequency and go brup, and then brup, brup. And again, I didn't start high enough to be able to hit those low notes. Well, here's the problem. If you analyze all this by mathematics, you'll run into something that is mathematically identical to the Heisenberg uncertainty principle, which came out in quantum mechanics, and Heisenberg used it to show that if you're looking at a quantum particle, and I'm not a physicist, so I may misspeak here a little bit, but if you're looking at a quantum particle, if you know where its position is, you won't know how fast it's moving. And if you know its velocity perfectly, you'll have no idea where it is. So that gets transferred through identical mathematics over into this scenario, which tells us that we cannot know that at this instant of time, we have exactly that frequency. So these things would get blurred, smeared, smoothed out, just like we saw in our windowing analysis. And it's similar kind of mathematics, except it is fundamental here. So this Heisenberg uncertainty principle prohibits us from having this kind of perfect time frequency representation. So the first thing that people tried to do to get this kind of thing, this kind of time frequency representation, was called the short time Fourier transform. And there's some other names for it, and we'll run up against one of them in just a little bit. And I'm going to start off talking about continuous time just because it's a little easier to visualize it and see what's going on. So here's the signal that we're interested in taking a Fourier transform. And I've just written it out in terms of some dummy variable, tau. So that's really some time variable. And now I'm applying a window, could be a rectangle, could be hamming, whatever. And I'm going to slide that back and forth, and I'm going to use the variable t to put it into a certain position. So tau is the variable that it is varying over, and t is just a positioning variable. And then I'm going to take that product signal. So if this is a rectangle, it's really just moving a literal window through the signal and positioning it at each position. So hold t fixed, I've collected a certain range of that signal, and now I take its Fourier transform. So now I get a function of f at that particular fixed t. But now imagine changing that t to different values, and I get a whole time range of things. So if I were to plot that, it would be like plotting on this. Here's my time axis. Here's my frequency axis. So as I move that window through the signal, I'm plotting at different positions here. And as I plot that function as for a fixed t as a function of f, I'm plotting it along this range. So if I held this fixed at 3, a time of 3, I'd be plotting along like this. So that's where the frequency comes from. And that's called the short time Fourier transform. So here's a little picture. This solid curve is the signal. I'm showing it as a function of tau. And I'm doing this for a particular t value. So maybe like around 160 or so, wherever the center of that is where I might be referencing that little t. And you can see it's 0 out here and it's 0 out here. So it's not quite a hand or a hamming or a rectangle, but it could be any shape. And I just picked an easy to draw shape, some sort of trapezoidal thing here. Then when I do the product of them, this is what I get. So it's windowing and putting zeros out here. And so when I take the Fourier transform, it's just doing a spectral analysis of that little chunk. So this is just a mathematical mechanization of that idea of collecting a certain chunk of data and taking a Fourier transform, except now we can do it for a bunch of different values of t. In fact, we can let t sweep over a continuum, and we can get a plot that resembles this, but we won't get these nice sharp knife edges if we were doing it to this signal. We'd get some smearing, right? On a vertical line, instead of having a nice sharp edge there, that would get smeared out into a main lobe, and we'd get some side lobes up there and down there. We'll see some pictures in just a little bit. So the window function's job is to limit the range that the Fourier transform has access to, so that we have a time localized spectrum, and that's called the short time Fourier transform. Okay, now let's convert this to a discrete time version. I've changed some of the notation a little bit, and now instead of moving the window through the signal, I'm moving the signal through the window. And that's just a convenience for how we'll actually compute this with a DTFT, or a DFT rather. But it's fundamentally the same. And so R now sets up the length of the window and the duration over which we're observing. And N is a parameter that we use to move the signal's content in and out of the window. So now instead of moving the window, I'm moving the signal. Okay, so that's the idea. But the mathematics is pretty much the same. And so now I can interpret this. This was in terms of a DTFT, so I had that on a continuum. But in reality, I can compute only DFT of this. So we have the whole grid error issue, so we might want to do some zero padding. So I collect R samples, but I actually do my DFT computation with some zeros padded on. And so the effect of that is to change mathematically what happens there. But we know computationally how that works out. And it just gives us a closer spacing on this K. So we typically discard all the negative frequencies because they're going to tell us similar things that the positive frequencies tell. So we're just doing a single-sided spectrum. And now here's a new wrinkle here. Sometimes moving this ahead by one, I say move the window ahead, but in reality, just clicking the signal ahead one sample at a time, it's equivalent to moving the window one sample. So instead of moving it ahead by one sample, which might be a little bit of overkill, we might move it ahead L samples. Well, what's L? We get to pick that. And we'll talk about how we pick that L in just a little bit. Some of the possible choices. So now, instead of this clicking ahead by N, where every time N gets changed by 1, we jump ahead by L samples. So we're going to see that go through integers, 1, 2, 3, 4, but we have to imagine that it's really jumping in time by L samples every time. Okay, so the way that we think about L is usually in terms of the amount of overlap that two subsequent windows will have in common. So if we define the overlap as R minus L, here's a picture. So we often describe this overlap as a fraction of R. So we look at the overlap. So here, there's no overlap. So the total length that we collect, so in that case, R and L would be equal to each other. We jump all the way, no overlap between those two blocks that we would do subsequent DFT processing on. We hardly ever do that. So that's the other extreme, right? When we didn't have, when we did this part, we jumped ahead by 1. That was excessive in one direction, and now no overlap is excessive in the other direction. So now if we set L such that L is 3/4 of R, the amount of overlap is 1/4 of R. So we would call that 25% overlap is a common way to describe that. So we're moving ahead, but not as much as we moved ahead here, and there's a little bit in common. So that's a pretty common choice, 25% overlap. And then here, R over 2 overlap. So that means L is half of R. So we start here, we jump ahead by L. And so I should say this notation just means take the DFT of those samples. That's what that means. So this is in the time domain. So we jump ahead by L samples, which is R over 2. We have 50% overlap between subsequent time blocks. And so that's the idea. So that would be called 50% overlap. So the common ones are 25% overlap, 50% overlap, 75% overlap. But you can do whatever you need for whatever application you're trying to do. So keep that in mind. So here's a little picture to lay some of this out. I'm going to use 75% overlap, and I'm going to start with a ridiculously small block, 8 samples. We would never do that in the real world. And I'm not going to do any zero padding. We also would not do that. We almost always do zero padding. And so what I'm going to do is take 8 samples. So here's my X of n. Each star represents a signal sample. So I take a block of R samples and I compute the DFT of those. And I'm going to assume, I guess I don't really have to assume a rectangular window, but whatever window I apply, I now apply over those. If I were doing zero padding, I would tack zeros onto the end of that and then compute my DFT. But I didn't do it, so I didn't do zero padding, so I get 8 DFT points here. And I want a single-sided spectrum, so I did not do FFT shift, and I throw away everything except for the bottom half plus 1. So go back to the review video, I talk about that. And we can figure out what frequencies these correspond to because our spacing is Fs over 8. Same old as before. Where should this be located in time? Well, things may be a little different when you actually use these, but I'm just saying let's pick the middle of our window. And since I have 8 samples, there really is no true middle, so I'm just going to take 4. Really 4.5 would be more correct, right? Let me see here. I've got 0. I'm going out to 7. So really 3.5 might be more correct, but I used 4. It was just easier to notate it. So in a real application, it might use 3.5 or half values and things like that. So I compute this DFT, I extract the values that I want, and I'm going to plot those along the frequency axis at that time instant. Now I'm doing 75% overlap. So I move it ahead. In this case, that overlap is 6. So there's going to be 6 samples from the original that will get overlapped. So there's the 6 and then 2 more after that. So now I take another 8, compute the DFT, and extract the positive frequency side that I want. And where do those go on the time axis? Well, 6 is the kind of pseudo middle. So 6 times T sub S. T sub S is 1 over Fs. It's our time spacing. And so on and so on. So I would end up with an array of values that I then have to plot as some sort of image so that their values, their magnitude values, get color coded in some way. So that's how we do that. So first time point I'm just going to say is R over 2 times TS. So that's what I used. And the time spacing would be R minus the overlap times TS. So there might be some subtle differences when you actually do this, but this is what I did in this example. And our frequency spacing is our same old. Okay, let's take a look at this Heisenberg issue, the time frequency resolution trade-off. So you don't need to go to this Wikipedia entry. I'm not even sure these are still there. I grabbed these decades ago, but this is showing some computed examples for a signal. They're showing the signal in continuous time here, but obviously they had to compute this in discrete time. And so now we can see two different cases where we have different window widths. So remember, a shorter window is going to give us more broadening of sharp spikes in frequency. So from 0 to 5, we see a single sinusoid. So we should just see a spike at 10 hertz, right? 2 pi 10, that's 10 hertz. So there it is, but it's spread out. And then we should see one at 25. There it is, spread out, centered at around 25, but it's spread. So that's the uncertainty. I know that between these two time points, it's doing something 25 hertz-ish. There's some uncertainty as to what frequency it really is. Is it really a sinusoid at a single frequency of 25, or is it something that's spread over a range? I can't really tell. But then what ends up happening is if I go to a longer window length, so I let my R go larger. So R was the block size in our example here. So now I go to 1,000 milliseconds. So whatever that is for whatever sampling rate they used here, I don't remember. But now we see that there's less spread. So we had a lot of spread over here with a 125 millisecond, but now it's very tightly grouped at 25 hertz. So our resolution and frequency is much finer. There's much less uncertainty or ambiguity as to what frequency is going on in that interval. It's, pretty much 25 hertz. But look at what's happening. It's a little hard to see it here, but if we were to zoom in, we'd see that now there's some overlap along time. So if I were to zoom in on that, I might see that it's going along like this. And the other one starts earlier because it's longer and there's some amount of overlap. So when I'm computing things in this region, I'm getting both sinusoids, one at the beginning of my window and one at the end of my window, but I compute and I get both of those in my FFT. So there's some time uncertainty in this case. And in fact, if we just had a single sinusoid that turned on and then turned off, we would see that there is some uncertainty as to where that starts and stops. So that's the idea. So this short time Fourier transform is a great tool, and we'll use it in many different scenarios throughout the course, but it has some limitations. And there are some other tools. Wavelets are one. There are some other things like wavelets that have been used, but for audio, the short time Fourier transform is still holding its own as a way of thinking about how a signal's spectrum changes over time. So all the things we talked about at the beginning of the note set, the fact that we're going to collect a small amount of data, all folds into this thinking. It's just now that the blocks of data that we're imagining are moving so that we can see a time-changing spectrum. So we can almost think about this as a score for the music, although this is going higher frequency down, an actual music score goes higher frequency up. But someone could say, oh, play 10 hertz, then play 25 hertz, then play 50 hertz, then play 100 hertz. That'd be a little boring as music, but that's the idea. And that's how people use this short time Fourier transform. Now, this is also called the spectrogram. So MATLAB has a command that's called spectrogram, but in reality, it should be called STFT, short time Fourier transform. I think it does have another command called STFT that works maybe a little differently, but I would rely on the spectrogram. It really just computes the short time Fourier transform. So you put into here, I used a Y, it would be the X that we've been talking about. You can choose any window shape that you want, and you put in the window size right there. Now be careful, there is some interaction. If this is a row, This is going to be a column, and MATLAB will yell at you. So you might want to put a transpose there to turn that into a row. So just be aware of that. This is the overlap. I'll show you what that means there. And this is your FFT size. We'll talk more about that. And then finally, the sampling rate that this signal is been sampled at allows you to create the time and frequency vectors. And that array of DFT points is in the S, with down the column are the frequencies, and across down it are frequencies, and across it are time points. So that's the signal, that's the window type, that's the block size or the window length, the overlap in samples. So not a percentage, it's an overlap in samples. So this number here needs to be less than that number. And so if you put in R here, you would be complete overlap, and that won't go anywhere. So if you want to move ahead by one sample, you would put in R minus 1. If you want to move ahead 50% overlap, whatever R is, you'd put in half of it here, or at least as close to it as you can in an integer. NFFT is the FFT size with zero padding. So that number should be bigger than R. So usually 4x or 5x, and it doesn't have to be a power of 2, but it's common to make it a power of 2. And then Fs is the sampling rate. And then you get the short time Fourier transform matrix, and you get computed frequency points and time points relative to the sampling rate and the overlap and so forth, and the NFFT. So it figures that all out. So you run this command, you get those three things, and then this is one way to plot it. This is the way I like to do it. I use the surface plot. I put in the T and the F vectors that come out of here. You have to take the absolute value because this is the short time Fourier transform. Technically, the spectrogram is the magnitude squared of the short time Fourier transform. So this says spectrogram, but it really computes the STFT. So you have to take the absolute value here. Sometimes we want to do this in dB, so we would do 20 log 10. And then the edge color and the none are just things that I put in to make the surf plot look the way I want it to look. I do an axis tight that just makes it look the way that I want. And then view makes it look at this surface plot from above, so it's not really a surface plot. And it will be some appropriately colored scheme, and you can change the color scheme with color map commands and things like that. So just some terminology. Like I said, the short time Fourier transform is complex valued. The spectrogram is either the absolute value or the absolute value squared. I think it's usually the absolute value squared, but that's really neither here nor there. So technically, the spectrogram command computes the STFT. And like I said, I think there is an STFT command. I don't use it, so I would caution you. It might not be called the same way. And so that's it. So hopefully this gives you some insight into the ins and outs of DFT processing, and then some of the issues involved with choosing windows and using it to look at spectra of signals that are audio or music, and then using the spectrogram to see how the spectrum of a music signal changes over time. And I'll post another video that is an example of using spectrogram to analyze a little music clip of some music that I wrote a long time ago and recorded a long time ago, a little guitar piece. So check that out. So that's it.